Ok, já está a aparecer aqui. Já vemos muito bem.
Can I?
Yes.
Oh,
Say first.
okay. Hi.
Yeah.
So,
Welcome.
hi, Atira. Thank you for the invitation. So, good morning, good afternoon, everyone. My name is Catarina Barata, and together with Rita, we will be presenting a little bit of what we have been doing with computer vision in healthcare, mainly using graph-based learning, but also.
Catarina, one moment. Sometimes it's a very noisy when you come very close to the system.
Okay. Do you think that it's better like this?
Yeah, this is
Which
better.
might-
Yes.
Okay, great. So mainly using graph-based learning. So just to give you an overview, this might seem slightly different from the works in robotics, but actually robotics fits in this context, and several of the things that we do here also work for robotics. Our field is that of digital health, where we have an healthcare institution with a database of patients. So we have history of the patient. We have multiple kinds of data with different characteristics. So basically we have challenges everywhere all at once, which means that we are working with longitudinal data with different timestamps, missing information. That might happen with sensors as well. Data with different properties, so tabular data, time series, reports that fit in the natural language process field, medical images, and inside medical images we have 2D data, 3D data, images at the cellular level, macro images, so it's a mess, basically. And what we have been working on is how to integrate all of these into something that we can use to represent patients, to make to make actionable decisions for the patients, to support clinicians in their tasks. And one of the things that has been critical for our work, and that's why I decided to show here, is that as in the field of robotics, in the field of healthcare, we don't have much data often. So we rely a lot on this concept of the foundational models that are very good feature extractors. And nowadays, luckily, we have foundational models in different contexts of medicine. And we then start from here to actually do a lot of our work. So the things that Rita will show next, actually, we rely on foundational models first. And for vision in particular, it's very funny what's happening in the medical field. So we have foundational models with different degrees of specialization. So we have what we call the medical foundational models that work with supposedly any kind of medical imaging. Then we have modality-specific foundational models, for example, for MRI or for pathology data like we have here. And then we have, for me, those at the bottom are no longer foundational models because they are task-specific, so it kind of disrupts a little bit the concept of the foundational model. And this is a warning for anyone using foundational models, because foundational models are not only part of the medical imaging field, they are also general to other contexts and in robotics. So the concept of VLMs, for example, is being used a lot, is that the foundational models must be picked very carefully, because if you pick something that is very narrow, in terms of the way it was trained, it might not generalize that well to a task. So sometimes it's better to go for something that is more general. Other times it's better to go for something that is more task specific, and it depends a lot on the application. One of the things that we are very interested, like I told you in the beginning, so when we look, it's the idea of time. So everything that we collect from a patient has a certain structure. And that structure is usually a timeline. It's not a very beautiful and uniform timeline, but it exists. And the other kind of structure that we have is inside the data itself. So Our medical images are highly structured, which means that we won't be our human body has a certain anatomy, so things won't change places across images. But that's something that we usually lose when we just use foundational models without any care. So something that we have been focusing is how to impose structured representations inside the features that we collect from the foundational models. And now I'll pass the word to Rita.
So a solution to include this spatial information is graph neural networks. And before explaining how do they work, I will first explain what is a graph. So graph is a set of nodes and edges that connect different nodes. In graph neural networks, we received a graph and then we go through 4 different steps. So the first step is message passing, where we aggregate information of the neighbors and the node itself. So here we are focusing on node 1, and so node 1 will receive the information from node 4, from node 3, and from node 2. And then it will aggregate the informations of the neighbors and update the information with the information of 4, 3, 2, with the node 1 itself, and then we update the information of the node 1 with the information of its neighbors. So an overview of graph neural networks. We have different layers, so layer 1 and layer 2, and each layer we update the information of each node, as I've explained previously. So here, basically, we are updating the information of node 2 by combining the information of its neighbors. So we obtain a new representation, and we do this to all the nodes in the graph. In the second layer, basically, we update the information based on the neighbors 2 hops away. So we update the information of this node, and this node based on the neighbor information. Then we have a final graph level representation where we use it to predict. So here, moving on to the prediction part and to my PhD work. In my work, I'm focusing on whole slide images, which are pathological images that contain different zooms and levels of information from the level part from the whole slide image, the total image, to the nuclei information. So basically, in my work, I receive an image and I try to make it a graph. So by removing the background information and then by making patches, and each patch will then be resumed to a vector, and I work in the feature level by aggregating the vectors that are neighbors. Then I train my model and I try to predict the survival of the patients of 12 months. As Professor Catarina already said, that time is quite important. Now moving on to another work that we have here and shows different application of graph neural networks. So here we are trying to recreate what is happening in a doctor's appointment, where the doctor sees the patient in different timestamps. So we combine different informations using the graphs. So in this first part, we receive demographic information, cognitive information, and images, MRI and PET information, and we combine it using time. So here, it's the first appointment of the patient and the second, and so on. And we can combine graph neural networks using other types of models, such as gated recurrent units. Here I tried to amplify the applications of graph neural networks. So we can use them using human motion graphs, as well as robot kinematic graphs, social media, where each user is a node and the edges are like the likes they have in common. And for example, for traffic forecasting, we can also use graphs.
Finally, and this is a project where we will also be using graphs to actually model time and transitions in images. This is a project that bridges healthcare with robotics. And basically, the idea in this project is that we are developing vision models for processing surgical videos, and our end goal is, besides predicting patient outcomes, as usual, we also want to use the data that we collect from these videos to not only train doctors, but also to train surgical robots. So that is the end goal. And for this, we need to answer different research questions. So how can we summarize these videos into the relevant content? Because some of these surgeries can take, for example, up to 2 hours, and we have a frame rate of 25 frames per second. So a very high load of information. How do we model? And that's where, for example, the affordance model comes into play, the relationship between tools, organs, so the surgical tools that the surgeon is using, the organs and the actions that the surgeon is performing, like is in the figure here, how to predict patient outcomes from the videos, how to generalize across centers. So we have several research questions. I will just show an example. So this was a thesis that was done here at IST that was presented in June, where Carolina was trying to take, so this, all of these rows, this is the same video and this is a sequence of frames, and she was using unsupervised summarization methods. On the left, just K-means clustering. On the right, it was methods based on generative adversarial neural networks and reinforcement learning, and she was trying to identify key frames in each stage of the surgery for then to give to the physician to annotate and to validate. And as you can see, there is a lot of difference between just doing K-means and more advanced things. And this is a work that is ongoing now, and I don't think that, oh, this was supposed to be a video, sorry, it's not working. But this was a video, a short clip of a surgery where these blue arrows that are here are the optical flow. So something that we are trying to capture is both the motion of the camera, because during these surgeries, there are 2 people working, one with the camera and another one with the tools. And we are trying to use things like optical flow to capture the motion of the 2 doctors that are interplaying in the surgery, to understand their connections, to understand how they work. And actually, this project, I also decided to mention it because I believe that one of the students from your institute will actually come here for a few months to do an internship, and it will be helping us solve some of the challenges of this project. Let me come back here. And so thank you. If you have any questions, we will be happy to answer.
Okay, thank you very much, Catarina and Maria. So any questions? Yeah, please come forward. Yeah. Yeah, I can.
Professor, I have a very small but general question. You see, when I was a kid, I've heard about this kind of robots called microbots and nanobots. These are the kind of bots that we're talking about bots that are in the order of a few nanometers, so small that you could literally load them into a syringe and insert them into the body. Once inside, these bots, which are pre-programmed to do the particular surgical tasks, will carry it out. Is it possible to actually take these nanobots and apply an algorithm like GNN on them in such a way that accuracy in which the surgery on that particular affected body part can be performed?
Okay, that's an interesting question. If we can use graph neural networks to, so the idea would be to track the nanobots, to evaluate their performance, to model their interaction. How would it work? Do you have a guess?
Mm, mm, Generally, we prepare the nanobots with a set of heuristics and instructions. That is, if it encounters that particular affected body, like let's say a tumor or a deformation, the particular set of rules that it's trained upon to fix, it will execute that once it is in that particular sector of the body. Mm.
Okay, so they are programmed to go to a certain place in the body. Yeah, we That's an interesting question. Maybe we could, like, each nanobot is a node.
Yeah.
In the graph, right?
I think we could do it, yeah.
Yeah, each of them would be like a node in the graph, but then
That's it.
their relationship, so the edges probably wouldn't map to spatial locations like the ones that we have here, but they would need to
Interaction.
to map to some sort of interaction between the bots and, for example, the anatomical part or the task that they need to do.
Yeah. Okay, I don't have any more questions.
Okay, thank you, thank you. So it's a very good thought, maybe leading to some good research as well. So yeah, so one more question from my side. So you were showing some image on the surgical video, right? So are you using only the sensor? Which sensor are you using in particular for that? Those images?
To acquire these images that we have
No,
here.
the previous one. Yeah, this one. So are you
This one?
taking the previous one, previous slide? Yes, here. 36.
No, it is 36. Yes, this one. Yeah.
So are you taking the human motion videos as well?
Not in this surgery project. We have another. So this is a public data set, the one on top. There was a master student trying to model the position of the surgeons inside the surgical theater. He has to model a little bit the way they interact. But actually, this is related to another thesis that me and Plinio are co-supervising, where the student is trying to split training of CPR. So yes, CPR. And evaluate the training sessions based on the positions. And yes, here what they do is they use cameras, and then they collect the skeletons using something like, I think that, for example, our student is using media pipe to get the skeletons, if I'm not wrong. And then they also use audio information. So actually, these are very rich. But for these data sets, the one that I'm showing here in the figure, this is a public one. And I don't think that they used media pipe. I don't remember. Do you remember, Plinio, which one they used to acquire these skeletons? Yeah, I don't remember. But it was something in, or open pose, something in
Open
that
pose,
line.
maybe, yeah. Open
Yeah.
pose with media pipe, you mean. Yeah.
This is not Kinect, that I'm sure, or real
Okay.
sense, yeah.
Yeah. Okay, thank you very much, Catarina and Rita.